Hi, welcome to the next of our series of Practical Electromagnetics for Engineers. Today we're going to be talking about some of the properties of one solution to Maxwell's equations, which are plane waves. Remember from last time we derived from Maxwell's equations the wave equation, and we saw that propagating sinusoidal waves were one possible solution. If you're in my class, you can follow along in section 7.2 of the textbook. Just to remind you, we have four Maxwell's equations, and they come in two different forms. The differential form, which is useful for solving fields extended over an area because derivatives aren't defined at points or discontinuities, and integral forms, which are more useful for solving things where you have discontinuities like wires or points and things like that. The four equations are given right here, and we're going to see these over and over and over again. And remember, last time we combined these two equations to develop the wave equation. And we saw essentially that one solution to Maxwell's equation, given by the wave equation, is an electric field that varies sinusoidally in time and space. And you'll notice that I've given a slightly different form here that involves vectors, a vector for k and a vector for r, because this is the general form that gives the equation for a plane wave anywhere in space at the point r moving in the direction k. So k is called the wave vector, and it says which direction the wave is moving. And remember, we derived an expression for k last time, and all I've done is turn k into a vector by using the unit vector k in the direction the wave is propagating. However, we also talked about how this solution was really only completely valid under a couple of assumptions. That the permittivity doesn't vary in space and the permeability doesn't vary in space. In other words, the material is what we call isotropic. There's not spatial variation. There's no free or movable charge that can be pushed around in the fields in the region we're talking about. And also that the material is not conductive, or the conductivity is zero. And this solution describes a wave that moves in free space exactly the same way waves moved on wires way back when we were talking about transmission lines. And this is actually important because, as electrical engineers know, we get signals from place to place on wires, but Maxwell's equations and the wave equation says we can also get signals from place to place if there's nothing to carry the signals. They're propagating through vacuum or through free space. We're going to spend a lot of time on this and try to see plane waves from a lot of different perspectives, including some animations. But generally, the solution looks like this. You have a wave that's propagating the direction given by the vector k, where k is given by this expression right here that is determined by both the frequency omega, 2 pi times f, as well as the properties of the material, mu and epsilon, which of course we know are isotropic. In the plane orthogonal to the direction the wave is traveling, or the plane orthogonal to k, the value of the electric field is constant. The electric field is a vector, and it points in some direction, as I've indicated by this vector right here. But the vector field is going to be constant everywhere in space. So if you looked at this point out here, it would also have a vector that pointed in exactly the same direction, was the same magnitude, anywhere on this plane. And of course, E is going to vary sinusoidally, because that's what this expression says. This exponential term is a sinusoidal variation. And so if we move this plane, we might expect the magnitude of E to change. Now, because vectors tend to confuse things, we can simplify the solution, essentially, by making an assumption that the wave moves in the z direction. And this is a perfectly good assumption because we're allowed to rotate our coordinate axis so our z-axis lines up with whatever direction we choose. This is a general property, the rotational symmetry of coordinate axis, that we're always allowed to do. And so this is perfectly good. And in this case, the electric field is going to point in some direction of the xy plane, and essentially, although it varies sinusoidally, the magnitude of the electric field is going to be constant everywhere in x and y. And in that case, we simply replace k dot r with kz, and we simplify k, and it's no longer a vector. Now, we're going to spend a lot of time looking at what these solutions look to be and try to get them in our head, because they're not at all necessarily intuitive. They're not things we see in everyday life. And so we're going to look at some animations and various things, but let's start fairly simply at what this solution looks like to this equation, essentially right here. What we have is a equation that says things vary sinusoidally, both in time and in space. The wave's moving in the direction k, so you can think about things going in that direction. It turns out that, in fact, at every point in space, there's going to be an electric field. It may have the value 0, but it's going to be defined at every point in space. And at this point right here, the electric field goes in this direction. And in the plane that's orthogonal to k, which I'm trying to draw here, the field is going to have a constant value and a constant direction. So at this point in space, you'd also get a vector that pointed exactly the same as that vector, and the magnitude of the electric field at this point in space would be the same. However, when you come over here, the value would be negative. Here, the value would be 0. So there is some constant value of the electric field at every point in space, but that value varies both with space and with time. So let's dig into this a little bit more by making a simplifying assumption that will help us understand this a little bit better. That assumption, in order to simplify the solution, is assuming the wave moves in the z direction. And this is a perfectly good assumption because, remember, we're allowed to rotate our coordinate axes however we want and translate them or move them in space. This is a valid thing to do. So we can always just rotate our coordinate axes so the direction of the k vector is along the z-axis. In this case, the electric field points in the xy plane and the wave moves along z, and instead of that dot product between k and r, we just multiply kz, and we just take the magnitude of k. And this simplifies things a little bit. So let's take a look at the solution here. We're simply moving in the z direction. We know things move sinusoidally in z. We've essentially frozen time, so we've chosen some t prime or t naught, and are not looking at the temporal variation because I can't do that except in a movie, although we will in a little bit. And we're going to look at how the wave varies in z. At this point, we see essentially that there's a positive value at that point in space, at this particular instant in time, and a negative point here. The green plane, which is the xy plane, because that's orthogonal to z, has a constant value, a vector field pointing all in the same direction at that point. A negative value is going to appear where the wave has negative values, i.e. in the red plane. So one way to think about it is we just basically draw those vectors on. And if we were essentially creating a vector field where all the vectors point, as is shown right here, to sort of the positive x, positive y direction, at the point the wave is positive, at the negative point of the wave, those vectors are going to be negative, and we know a negative of a vector just points in the opposite direction. So you get the sense that although the vectors are constant at any plane in space orthogonal to the direction of propagation, or in the xy plane in this particular case, that the length of those vectors and the direction of those vectors can vary depending on whether the value is negative or positive. And we'll see some examples of this later on. As we move forward in space, you can see that the values are going to repeat themselves. Essentially, you're going to get the same values on every green plane that corresponds to a positive peak, the same negative values on every red plane that corresponds to a negative peak, in between values that is on the wave. And so the plane wave is just going to repeat itself through space, and at any plane orthogonal to the direction of propagation, or in this case in any xy plane, there's going to be an electric field in space, but it's going to be constant no matter where you go on that plane. Now, as I mentioned, even with the simplified solution here, it can be very hard to visualize plane waves in 3 dimensions. So essentially what I'm going to do is I'm going to go to a pre-existing simulation that I use in my classes a fair amount at Fallstad, and basically use the wavebox simulation. If you'd like to go and play with this yourself, this is the URL to go get to it. And so I'm going to basically insert another video here I recorded how to use that to look at some of the variations of a plane wave in 3 dimensions that is also varying in time. Hopefully this will give you a little bit of insight into what these solutions look like.
So if you go to that URL and enable Java, you're going to see an app that looks like this. It'll pop up in a new window. I'm going to scroll down in the setup box to choose plane wave. And this doesn't look like much. I can change the simulation speed. I can change the brightness of this. I've already increased the image resolution. Let's drop the frequency a little bit. And you'll notice how hard it is to visualize plane waves. But let's rotate this box. Notice I can rotate this freely around. If I look at it in the right plane, this is what plane waves look like in time and space. You notice you have regions where the field is constant, although things move in time. If I assume green is positive and red is negative, the field alternates between those and moves. If I rotate this in different directions, you'll see that and get the idea that in the x and y directions, the field is constant. It has the same value even though it's changing in time and changing in space, but that spatial variation only changes along one axis, which is the way we wrote the equation, is the z direction. So if I look at the right angles like this, everything looks homogeneous. But if I look in alternate directions, I can see why we call these plane waves, because they're planes of field, magnetic or electric, that move through space. And again, I would urge you to go ahead and log on to that website, choose plane waves, and play around with it. You can do things like increase the frequency, which you see puts the planes closer together, decrease the frequency, which moves the planes farther apart, and you'll really get a good idea of what plane waves look like by going to this visualization tool.
Well, hopefully that video gave you a little bit of insight into maybe what a plane wave looks like in three-dimensional space that's varying in time. And we've talked a lot about the plane wave solution, and we'll talk more about it, but I want to go into a little detail on why plane waves are useful and to understand this a little bit. You may think that they're not so useful, because if we think about a source emitting electromagnetic radiation, all sources essentially are going to emit things that aren't planes, because sources are spatially limited. We think about a point source, which is a source that emits at one point in space. And just with the analogy of dropping a pebble in a pond, you can think of this source emitting spherical waves that go out in multiple directions. And obviously, these aren't plane waves. These are essentially circular waves. So why is this plane wave solution useful when sources generally don't make plane waves? Well, it turns out that if you go far enough away from the source, so travel all this distance out here, over a fairly small region, even though the wave has a little bit of curvature to it, it is pretty much like a plane. So you can look at any section here and say, you know, that pretty much is like a straight line. And so for an observer at some point far away from a signal source, the signal they're going to detect is going to be a and so you can essentially say that plane waves are good approximations when you're far away from the source of the electromagnetic wave. And there's another really cool feature of plane waves that we're not going to delve into in this course, but is going to become really important if you go on and study this in more detail. And that's that the property of superposition holds for plane waves. Remember, superposition holds for electric and magnetic fields? We saw that before when we were looking at static fields, and it turns out superposition also holds, in most cases, for time-dependent electric and magnetic fields. And so we know through the Fourier theory we can build nearly any signal whatsoever by summing up a bunch of waves. So the really cool thing about plane wave solutions is that if you sum up enough plane waves, you can build up any spatially dependent or temporally dependent waveform whatsoever, and this is the heart of electrical engineering. This is essentially using Fourier series and Fourier transforms to understand how to do that. The key message is here. If we solve for one plane wave, and we know what's going on with one plane wave, as long as our systems are linear, we've solved for practically any system whatsoever, or any signal whatsoever. Again, the linearity holds for this, but it's a really, really useful thing to do to solve for plane waves. I want to take you back a little bit now and show you a slide that was in one of our first review videos where we talked about waves. Plane waves, like any other wave, have amplitude and phase. The amplitude we can express just as a number. The magnitude out there is essentially the difference between the peaks of the wave. So this is essentially the magnitude of the wave. Technically what happens is the magnitude is defined by the value from here to here, so that would be the value m. This distance would be negative m. Remember that the phase of a wave is the position we are on the wave. And so the phase varies both with space and with time. We can think about the difference between two peaks in time as being the period of the wave, t. This is all review. And so the frequency is just 1 over the period. The radial frequency is 2 pi over the period. And we know that really the amplitude or magnitude of the wave is the number in front, and the phase of the wave is given by everything in the exponential, and that frequency really is just the time dependence of the phase. So the rate of change of phase with time gives us the radial frequency. There is really no such thing as frequency. There's just time-dependent phase. Similarly, the spatial variation has exactly the same types of math involved with it. The distance between the peaks, rather than the time between peaks, is given by the wavelength lambda, and the k vector is just 2 pi over lambda. And so the k just gives the spatial variation of the phase. Again, we have this type of term right here with a magnitude and a spatial phase. And instead of the time dependence, this should actually read the spatial dependence of the phase. But the spatial dependence of the phase is essentially the k vector. So k simply tells us how the phase changes with space. And you can also see that there are relationships in the phase. That phase essentially relates space and time on waves. And you can see these relationships that connect how fast the wave is moving or how fast the phase moves with omega, with k, with the properties of the material, the permeability and the permittivity, as well as the frequency. And these relationships are good to understand and good to memorize because you're going to get a lot of problems in life where you have to convert between one and the other. And understanding k and omega and the phase velocity really helps you understand waves. And some of you may be wondering about something, which is that we've solved the wave equation for the electric field, and we've seemed to have neglected the magnetic field completely. Well, it turns out you can do exactly the same type of calculation to derive the wave equation, except instead of deriving it for the electric field, you can derive it for the magnetic field. We also know that there are relations between the electric and magnetic field, and I've simply pulled the mu and the epsilon out explicitly here using some of our approximations or assumptions. And it turns out it's not really worthwhile to solve the wave equation all over again. But for plane waves, there's a very clear relationship between the electric and magnetic fields, and they're given by this expression. So it turns out that if the electric field has a y component, the magnetic field will have an x component. It's orthogonal to the electric field. So let me say this again. Magnetic and electric fields are orthogonal to each other in plane waves. They're perpendicular. And we would, of course, expect this because the electric field is determined by the curl of the magnetic field, and we know that cross products give us things that are orthogonal. So we'd expect, just from Maxwell's equations, that electric and magnetic fields would be orthogonal to one another. It turns out there's a relationship which is given by the square root of the permittivity divided by the permeability. And essentially what we do is we find out that if we take the square root of mu divided by epsilon, it gives us a value in terms of ohms. And this is called the impedance of free space. So now I take you way back to when we were talking about transmission lines, and we defined impedance as the relationship between voltage and current on a transmission line. There's a clear analogy between electric and magnetic fields, and the impedance of free space just tells us the relationship between the magnitudes of the electric fields and the magnetic fields. We also know that magnetic fields and electric fields are orthogonal to one another, so y components of E give you x components of H. Similarly, x components of E give you y components of H. And now let's take a little dive into an animation of electric and magnetic fields so we can understand and see what these look like with a moving plane wave with orthogonal electric and magnetic fields. If you'd like to follow along and play with this animation yourself, this is the website I got it from.
This is one of the various online applets you can find about plane waves. Essentially what I'm going to do in a second is I'm going to start this green dot moving up and down, and it's going to pretend it's the source of a field. And it's going to create electric and magnetic fields. The electric fields are shown in red, the magnetic fields are shown in blue, and you can already see here that these fields are going to be orthogonal to one another. So let's go ahead and start this and see what happens. The green dot moves up and down, generating an electric field. The blue dot moves side to side, generating a magnetic field. And essentially what you see in this, hopefully, is that the waves are propagating along the z direction, our electric field's in the x direction, and the B field is orthogonal to it in the y direction. So for the plane wave solution, electric and magnetic fields are orthogonal to one another. Hopefully this gives you a better sense of the spatial variation of electric and magnetic fields.
Hopefully that little side video helped explain how the electric and magnetic fields are related to one another. It turns out in the general case, if you have a plane wave propagating in any direction, not just along the z direction, the relation between magnetic and electric fields are given by these two expressions right here. It's just the cross product between the unit vector that describes the direction of propagation of the wave, either divided or multiplied by the impedance of free space, which again is given by this term right here. And if mu is equal to mu naught, epsilon equal to epsilon naught, it turns out this impedance is 377 ohms. So let's go ahead and write that the square root of the permeability of free space divided by the permittivity of free space is equal to 377 ohms. A good thing to remember. So let's just wrap up with a quick summary of plane waves. Essentially, we saw that if we rotate our plane wave so it's propagating along the z-axis, we get this solution for the plane wave. This corresponds to a wave moving in the z direction where there's a vector field, the electric field vector, at any point in space is constant in xy, constant in the plane that's orthogonal to the direction of propagation. The electric field varies sinusoidally both in space and time. So at this point in space and this point in space, you're going to have different magnitudes and directions of the electric field. The animations really help clear that up. That essentially what you have is that k gives you the rate of change of the phase of this wave in space, and these are some expressions for k. Omega is the rate of change of the electric field or this wave in time. The ratio between omega and k essentially is the rate of change of phase in time divided by the rate of change of phase in space. And this, as you can see just by doing the simple math, and as we talked about before when we were talking about waves, gives you the phase velocity of the wave. So omega and k determine how fast the wave is moving. And of course, we know that these are also equal to the square root of mu epsilon. So there are a lot of tight relations between the omega, omega, the temporal rate of change of phase, k, the spatial rate of change of phase, how fast the wave is moving, and the properties of the material that the wave is propagating through. One last thing that needs to be mentioned that's a very useful approximation is that in most insulating materials, mu is equal to mu naught. In that case, we can rewrite the phase velocity a different way that's actually much more useful to engineers. We essentially say that maybe there's some relative permittivity, epsilon r, and we're going to pull that out of our expression right here. And then since we know 1 over the square root of mu naught epsilon is equal to the speed of light, we can write the phase velocity of the wave as c divided by the square root of epsilon r. It turns out that this epsilon r is given another variable because it's that important, and it's called the index of refraction, which is given by n. So n is the square root of the relative permittivity. And essentially, if you know the index of refraction, you know how fast a wave is propagating, or at least what the phase velocity of a wave is through a given material. And we're going to use this a lot, and you're going to see this a lot when you talk about the propagation of waves through materials. Generally, you use the index of refraction more than you do the permittivity.